In this video, we'll be discussing remedial measures for simple linear regression, specifically looking at different transformation options that we can utilize. So for transformations really are just changing the variables that we're using in our regression model to be different variables. So for instance, instead of regressing x and y, we may use x squared in our regression model. The best transformations are those that are selected from theory, not just statistical theory, but theory related to the data context. So for instance, if I'm looking at the square footage of the house, I might choose to use a transformation that relates the square footage to regular footage, so maybe the square root transformation. Some of these things may or may not be appropriate, and this is why it's really important to have context of the field that you're studying for some of your statistical analyses. Typically, when we're working with clients or for a boss, those are fantastic individuals who you can ask for the nature of underlying relationships, and they might be able to tell you things like, oh yeah, of course, blank is related to the natural log of blank other variable. You'd be surprised how often sometimes this happens. However, many times this isn't available. So in this class, we're going to focus on more generic methods that are based on statistics and data patterns that we may see. However, it is preferable to use theory of the data context if possible. So we're going to talk about the more generic kind of data-y version that data drives this. But there are benefits to that. That is, we don't have to know the data context. There's also some detriments to that where we would prefer to know the data context and implement something that is theoretically valid and makes sense. Generally, our overall method is to take educated guesses at the transformations and then try them to see if they worked. So for instance, I may look at a plot and kind of shrug my shoulders and say, well, I think the square root transformation will work. And then I implement the square root transformation, rerun my model, and determine, did it actually fix my variables, yes or no? If it did, then I would say that the square root transformation was effective and keep it. If it didn't, then I would view the square root transformation as ineffective, and I wouldn't keep that. I would go back to my initial model and maybe try a different transformation, and recheck the diagnostics to see if it worked. Finding a good transformation is as much of an art as it is a science, especially when we're looking at plots. Realizing how to interpret them and looking for data patterns just takes time, but that said, it does get easier as we practice over and over again. You'll be able to start identifying different patterns in residual plots and in scatter plots that you can use to specify which transformation is the most likely to be effective. Now we can transform X or Y. Either one really are options that we can select. It really depends on what our goal is, and actually we'll talk about right now when we would choose X versus Y for our transformation. So it's important to realize that actually transforming X versus Y, sometimes they fix very, very, very similar problems, and they're just two different approaches that we can use. They aren't particularly interchangeable. We'll talk about that in just a second, but the problems that they address can be very similar. For instance, nonlinearity is one that both of these address. And what's kind of interesting is that if I'm addressing a nonlinear relationship, I do different transformations for X than Y. And we'll actually demonstrate that graphically in a future slide. Now it's important to realize, and we'll talk about this too, that transformations in Y affect more than just Y. So when I'm transforming Y, I pick those particular transformations because they affect something else in addition to affecting the Y transformation. Now, when we're looking at transformations with X and Y, it's important to realize we can do multiple transformations. We can transform both X and Y. We can do multiple different transformations on X or Y. And sometimes when we're trying to address complex issues, these approaches using multiple transformations can be used. It's not particularly preferable unless you have a really good reason, and we'll discuss that later in this lecture as well, this video. So recall our model, y equals beta 0 plus beta 1x plus epsilon. And consider a pair of transformations for the square root relationship between x and y. That is, you're going to have your plot, and it's going to have kind of an upward but ever decreasing curve. So that's the square root graphic. That's what we're trying to model. Now, if we were trying to model that, we might use the transformation going from x to the square root of x. That is, instead of putting x in the model, we now put the square root of x in the model. And literally what this involves is, like in R, you take the square root of x, write it as a new variable, and then include that variable in the model instead of including x in the model. So it literally is making a new variable square root of x and including that new variable in the model. So this is the way in which we could account for the square root relationship by doing a transformation of x. Now, to do this for y, instead of taking the square root of y, we would have to take y squared. Now, think about why this is. So this is the model. We get y squared. Why this is that when we solve for y, then we get y equals the square root of all this stuff, including x. So we've got the square root of x on the right-hand side, and this kind of has the square root of x on the right-hand side there, kind of too. So this is why the transformation in y is different than the transformation in x. But it's important to note here what else is going on. I mentioned in the previous slide that when we transform y, it doesn't just affect one thing. So when we transform y, it doesn't just affect the linear relationship between x and y. When we transform y, it also affects the nature of our errors. And so this is a really, really important consideration, that we'll use transformations in y when we're trying to fix the error terms, and we'll use transformations in x when the error terms look okay, but the linearity is messed up. So let's look at this graphically. I'm going to have two graphs. We're going to have a graph here and a graph here, one on the left, one on the right, and we'll see that both of these look like a quadratic relationship, an upward facing curve. This is a quadratic. And we've got, as x increases, y increases by an exponent of x. So in this particular case, in one, I'm going to choose to transform x, and in one, I'm going to choose to transform y. And this has nothing to do with the nature or the linearity of their relationship, because in this case, both of these have the exact same relationship. What this is going to do with is, do I also want to change the error term? So if I look at the error term here, I'm just going to look at the distribution of the residuals around this value. And what I see is the distribution of the residuals, well, they seem to have roughly equal variance all the way up the line. Now, I get the data that are more densely packed on the right-hand side than the left side, but we don't have any assumptions about data density. We have it on homogeneity of variance. So I'm looking at the vertical distance at each of these x values, the vertical distance, and for each of these vertical distances, the vertical distance seems roughly the same. So this says roughly homogeneous variance on the left plot. Now on the right plot, I see that my variance terms are much, much closer together on the left-hand side, very close together. And then as I move towards the right-hand side, the variance terms are much, much higher. The distribution of the residuals about this line is much, much wider on the right-hand side than the left-hand side. So this is the primary difference between these. Both of these seem to have a quadratic relationship. But on the left-hand side, my errors look fine. On the right-hand side, my errors need to be changed. So the equation that I would use on the left-hand side, because I would just want to account for the nonlinear relationship, and again, recall this is nonlinear relationship, a linear model, so this is still a linear model because my betas don't have any exponents or weird stuff going on with them. But I'd account for the nonlinear relationship by including an x squared term in my regression model. So that's the way in which I would approach it here, because I don't want to change the errors. The errors actually look, I don't know about normality, but at least in terms of homogeneity of variance, the errors look fine. Now on the right-hand side, I not only want to address the change in normality, but I also want to address the change in the error distribution. So I'm going to implement the function on y. I'm going to take a transformation of the y values and hope that when I fix the error term after transforming y, that's also going to address, when I fix the linearity term after transforming y, that's also going to address the error residuals. You'll see actually this is a common plot when the y needs to be transformed, especially with this square root transformation of y, that the errors start small and then get wider in this megaphone shape. Megaphone just meaning starting small and broadening out, and then funnel's kind of the opposite. You start broad and come in. So this is kind of a megaphone shape, not in terms of the line being curved, but in terms of the errors starting really close together on the left-hand side and then broadening out on the right-hand side like a megaphone does. Transformations in X. So for nonlinear relationships with a constant variance, that is, we don't want to change the variance term, and one other thing I should have mentioned here is with normality. So for a nonlinear relationship where my error terms seem to look fine except for the fact that our relationship is nonlinear, this is when we perform transformations on X. We'll tend to denote the transformed values as X star. And this works for X. This will work with Y too. You'll see Y star. So for instance, if I want to go from the model Y equals X to Y equals the square root of X, I'm going to say X star, that's my new X value, is the square root of X. And then I'll plug in the square root of X term into my model. And literally what we're going to do, as I said before, is we're actually going to create a new variable in R, define it to be the square root of each of the X values, and then we're going to use this new variable in our linear regression. That's how we're going to perform these transformations. Now for transformations in Y, we can do this for nonlinear relationships, but it's important to note that if we do it for nonlinear relationship, it's also going to affect the variance and the normality. So it's really important to realize that we don't want to address just a nonlinear relationship with a transformation in Y. We would look for a nonlinear relationship with non-constant variance, or a linear relationship that just has a constant variance issue. That's when we would look at a transformation in Y. Some common transformations we try are the square root transformation. And again, if I have my errors starting small and spreading out that megaphone shape, this square root transformation can help if my variance is increasing with X. And we actually saw in that previous graphic, the square root transformation for that previous graphic was the perfect transformation. It fixed the linearity issue, and though we didn't demonstrate it on the slide, it would have perfectly fixed the non-constant variance issue. Natural log is another option that we can try. Just take the log of Y. So Y star would be the natural log of Y. And this would be if we have that funnel shape. So instead of the errors growing and getting bigger as we move from left to right, let's say the errors started really big on the left and got smaller as we went to the right. So it kind of makes this greater than sign, or a funnel looking shape. That would be a good indicator that we would want to use the natural log function instead of the square root. Now if our pattern is linear, one thing that we may want to try out is the inverse function. This can be pretty handy. Just take 1 over y and look and see if that addresses the issue. So lots of different options that we have here, and actually we'll talk about a nice procedure for determining them in just a moment. So we can transform both. Consider a transformation of both x and y. What would this accomplish? Now think about what we would do and why we might do this. Let's say that I had errors, so I have a linear relationship, but my errors are increasing, so I've got this megaphone shape. Let's say I implement the square root transformation with y, so that fixes the errors, but now my graph is not looking appropriate. My graph is looking a little bit messed up because I implemented a procedure that affected not only the variance, but it affected the linearity. So what could I then do? Well, if I implement a transformation on y to fix things with variance and it messes up linearity, and if that transformation actually fixes the variance issues, then maybe what I want to do is use a procedure that just fixes the linearity issues without retouching that variance. So in that particular case, I may choose to do then a transformation on x as well, so that linearity gets fixed back to how it was, and my errors also stay how they are. So I would use the transformation on y to address the homogeneity of variance issues, and then redo or then implement a transformation on x in addition to the transformation on y to fix the linearity issues that happened when I fixed homogeneity of variance. So we talked in the previous video very briefly about the Box-Cox procedure. The Box-Cox procedure is a procedure which gives a suggestion for the very best transformation that we could select. Now, Box-Cox only looks at certain types of transformations. Specifically, it only looks at power transformations. That is y to the blank power. So that's all that Box-Cox looks at, to the blank power. That's it. So we can't solely rely on Box-Cox if we're looking at transformations that aren't related to a power of y. It doesn't really work for those. So Box-Cox is really, really, really handy, but it's not a perfect solution. Now, Box-Cox gives a suggestion. Sometimes students see a suggested value from Box-Cox and feel compelled to utilize that value. It doesn't work like that. Box-Cox's suggestions are intended to be guides as to reasonable values to try for transformations. They aren't intended to give you the single numerical value that will best work. So when you're interpreting the Box-Cox results, make sure you're interpreting them as suggestions as opposed to as answers or rules. Typically, Box-Cox is a great starting place. So if I have to implement a transformation and let's just assume that I'm looking at the graphics and I'm not seeing megaphone patterns or funnel patterns. I'm not really seeing any patterns in the data. I'm not seeing nonlinear, I'm just not seeing anything. But I know that I need to do some kind of a transformation to fix it. Box-Cox may be a natural place to start, where I just run the Box-Cox procedure, see what it suggests, and try out a couple things as some initial tries. If they work, fantastic. I found a transformation that works and fixes my issues. If they don't work, then I can use those as a list of things that I've already tried and can narrow in on some other procedures that maybe are more likely to work. Now, Box-Cox is going to recommend a lambda value. A value of 1 implies that no transformation is going to be needed. So sometimes Box-Cox can tell us you don't need to do a transformation. Now, software, specifically R, gives confidence intervals. Now, what we do with these confidence intervals is Box-Cox is going to select a single lambda value, and then it's going to give you a confidence interval. We never, ever, ever, ever pick that single lambda value recommended by Box-Cox. What we do look at is the confidence interval, and we try to find nice roundish numbers within that confidence interval, which can tell us which transformation is going to be the most effective. And we'll have an interpreting guide on the next slide where we talk about what the different numbers are and what transformations those different numbers recommend. Again, our goal is to pick a nice number within the confidence interval. Now, if there is no nice number within the confidence interval, that may tell us that a power transformation is inappropriate for the data. So we're looking within the confidence interval, looking for a nice number, and again, we'll demonstrate some of those on the next slide, to see what the suggested power transformation is. We do not use the point estimate. That is, we do not use the single recommended lambda value. We use the confidence interval to make the best guess that we can as to what a reasonable range of power transformations are, and then pick a nice number within that confidence interval to try. Now, we may pick the nice number that's the closest to the point estimate or the single lambda value recommended by the Box-Cox procedure, but we don't just use that single value recommended by the Box-Cox procedure. One thing I should also mention is that sometimes multiple nice numbers are within the confidence interval of the Box-Cox, and what that implies is that we may have multiple power transformations that could be appropriate. What I tend to do is select the power transformation that is closest to the recommended lambda from the Box-Cox procedure first, try that one, look at the results, see how well it works, and then go and try the other one. Look at the results, see how it works, or the multiple other ones. And then after I've run all of the different possible nice number transformations that I could do from my Box-Cox suggestion, that would give me a good idea of which of those functions the best. And recall, because they're in the confidence interval, all of those are reasonable values. One last note on these Box-Cox confidence intervals. If the value of 1 is inside the confidence interval and suggests no transformation, my default might be to lean on no transformation. Now this follows the law of parsimony, which indicates simpler is best. So I really want to lean for this simple model, the one that doesn't have any data transformations involved when at all possible. So if the confidence interval includes 1, what I'm going to take this as is a suggestion that I should not transform my data. Now Box-Cox can be applied to X or Y, but traditionally, and I would say almost only, it is applied to the Y variable. So that's what we're going to talk about. All right, now let's walk through a few of the interpretations. A lambda of -1 implies that we should raise y to the -1 power, or y star should be y to the -1. This is called the inverse transformation, and if you think of y to the -1, that just means 1 divided by y. That's what y to the -1 is. A lambda of -0.5 is the inverse square root transformation. So that's saying y star should be y to the -1/2 power. If you recall, y to the 1/2 power is just the square root, and y to a negative is 1 divided by that. So this ends up being 1 divided by the square root of y. A lambda of 0 is the weirdest one because this is the only one on this list that is not a power. I'll say this one more time. A lambda of 0, strangely, is not a recommended power transformation. What a lambda of 0 recommends is taking the natural log of y. So y star would be equal to the natural log of y. A lambda of 0.05 suggests raising y to the 0.5 power, or just taking the square root of y. So y star would be the square root of y, and this is the square root transformation. As we mentioned on the previous slide, a lambda of 1 implies no transformation. That is, we would raise y to the first power, which would just leave us with the original y value we had in the first place. Finally, a lambda of 2 recommends a square transformation. That is, y star equals y to the second power. Now I've illustrated a few of these very common values, but it's important to realize that these lambdas can be a variety of different numbers. So if I had lambda equals 3, this would imply a cubic transformation where I should raise y to the third power. So I really want you to understand that these lambdas are recommended powers to raise y to, which is why we call these power transformations and say Box-Cox only recommends power transformations. All right, quick summary. Nonlinear relationships can sometimes be fixed by a transformation of x. Now it's important to say sometimes. Transformations don't always work. But sometimes we can fix them by transforming x, and typically we do this with nonlinear relationships where our error terms look fine, because if we transformed y to fix it, that would have an impact on our error terms. Non-constant variance can be transformed, or can be addressed by transformation on y, but recall from the previous video that maybe the best way to deal with non-constant variance could be to use a model that doesn't require a constant variance assumption. Most models do though, so if we have a non-constant error or a non-constant variance issue, transformation is a pretty common approach. Non-normal errors can also be addressed by a transformation of y, but in this case, we have that generalized linear model framework that, again, we're not going to go into in this class, but it exists and it's out there and it's actually not too bad to use. It's relatively convenient, though interpretation can be somewhat irritating. So the non-normal errors are one where we could reasonably use just a different model, or we could use a transformation on y. Incidentally, for the nonparametric statistics class, non-normal errors is what nonparametric statistics excel at addressing. So we could very easily use a nonparametric statistics model, which, depending on which model we use, is really easy to implement and actually is really easy to interpret. So those generalized linear models can be difficult to interpret, but the classic nonparametric statistics are very straightforward, sometimes even easier to interpret than our traditional statistical methods. Again, remember that transforming y will affect normality and homoscedasticity or homogeneity of variance. And this can be good, but it can also be bad. So sometimes we want to fix both of those issues at the same time, and a single transformation can address both of them. In other times, we really just want to fix one, but when we make the transformation to fix that one, the other gets broken. So we have to make sure that we are testing each of our assumptions after we implement every single transformation, not just the assumption that was broken with the original data. The Box-Cox procedure suggests power transformations on y, and we just talked about some of the different specific suggestions, as well as the general rule by which you would interpret other lambdas that we didn't explicitly discuss in this video. Box-Cox is really useful when we're just looking for a general guide, but it doesn't cover all of the possible transformations. So sometimes being able to interpret the patterns can be helpful. That said, when you're not seeing patterns in the data, or when you're just looking for a place to start, Box-Cox is a very common way to go. There are cases where transforming both x and y, or performing multiple transformations on the same variable, can be extremely helpful. So be aware that we can combine transformations for a specific purpose. And it's important to say, as we said before, all of the assumptions of the transformed data should be satisfied. That is, after I implement a transformation, I should be able to do all of my statistical assumptions checks, and all of the assumptions should get a green light or a pass. If I implement a transformation, even if it fixed the original assumptions failure that I had in my raw data, it doesn't work unless all of the assumptions are valid. So we have to be really careful, especially with this normality and homogeneity of variance thing. It is very common that if you use a transformation to fix one, it will have an impact on the other. Now, there are pros and cons of choosing the transformations approach. Again, we've just had a pretty in-depth video looking at these. The pros are that transformations are popular. They're pretty widely used. You'll see transformations relatively often. It depends on the field, but certainly in economics, those guys transform the heck out of everything. So there's a very wide field of transformations, and many people do implement these. Also, transformations are pretty flexible because you can use them to address concerns with multiple assumptions. So I can address concerns with normality and homogeneity variance by using the same method. That's pretty cool. Transformations are relatively convenient, and what I mean by this is you don't have to know a whole bunch of super fancy statistics. So for instance, if I had non-normally distributed data, I don't have to go and learn an entirely new statistical method for dealing with non-normally distributed data. I can simply implement a transformation and use my old tried and true statistical methods. In that context, it's pretty handy. These are also very powerful, and what I mean by that is that they can address a lot of different issues. So if I have some data situations, I can use transformations to address a variety of these through a complex, through multiple different data transformations I can implement. I can address a variety of situations, and I can address some pretty complicated situations depending on how many transformations I'm willing to implement. So those are the pros. Those are the good things about data transformations. I will say I tend to not prefer data transformations when I can help it. I used them. I have used them. I still use them when I need them. But by default, I don't go to data transformations. Now, this is something that different statisticians, even different statisticians that I have worked with, heavily disagree with me on. So do understand that to some degree this is a preference thing. But as for me personally, I tend to prefer selecting a more appropriate statistical model. And one of the biggest reasons some of the biggest reasons I prefer to do that are listed here. Better models are better. Why would I use a model that assumes normality when my data aren't normally distributed? There are a whole lot of issues here that are kind of subtle, but one of the biggest ones, if we can dive into it just a little bit, is the fact that if I'm fixing something at the face value, let's say my data are not normally distributed and I kind of force them through this transformation to be normally distributed. Well, maybe there's a reason the data aren't normally distributed. And maybe the reason that the data aren't normally distributed is something that impacts my other assumptions, like homogeneity of variance or independence or something else. Wouldn't it be better to use a statistical model that accounts for the underlying reason as to why my data aren't normal, as opposed to taking my data and kind of cramming it into this normality box to make it work with this particular method? There are statistics out there that don't necessarily lean on some of these assumptions. So when the assumptions break, why not choose to utilize those statistics as opposed to trying to force your data into this box that it didn't fit in anyways? Another thing that is important to realize is transformations don't always work. Now, this isn't really a knock against them because no statistical method always works, but there are issues. In fact, there may be even many issues that can't be addressed via data transformation. And I say with a reasonable number of transformations, I mentioned that you could implement multiple transformations on the data, and you could do transformations on X and Y. You could do multiple transformations on Y or multiple transformations on X. That is absolutely something that you can take advantage of. But the more transformations you do, the more problems you'll run into that we'll talk about in just 1 second. So you kind of have to keep the number of transformations that you're doing reasonable. Typically, I shouldn't say always. There are some cases I can think of where you don't have to worry about that. But typically, you should plan to keep the number of transformations reasonable. And within a reasonable number of transformations, let's say no more than 2 transformations per variable, within that context, there are many issues that can't be addressed by transformations. So that can be a problem. We haven't really talked about overfitting the data necessarily. We will talk about this when we get into multiple regression. Overfitting the data simply means that I'm modeling so much information in my sample data set that it's not being modeled for the population. It's a bit of a complex topic. Again, we'll talk about it later, but it is a risk when we do these transformations. Consider that I do a whole bunch of transformations that are for my sample data specifically, but address some idiosyncrasies about my sample data that aren't present in the population. What ends up happening then is my statistical model is custom made for those sample idiosyncrasies, but when I introduce it to the population to do things like explanation and prediction, it does rather poorly because it is so heavily designed to model the idiosyncrasies of the sample that it actually misses the larger trends of the population. This is the overall concept of overfitting the data in statistical models, and is something that can arise when we're doing a large number of transformations. Interpretability, I put it in large, bold, italicized, underlined letters. Interpretability is the biggest struggle with transformations. Consider, if you will, if I took the square root or the inverse square root transformation of y, and then I took y to x to the 2/3 power, and that is what was needed to make my data meet all of its assumptions. Imagine how you would possibly interpret that as x to the 2/3 increases by a single unit. What is a single unit increase in x to the 2/3? The inverse square root of y increases by beta 1. Like, what could that possibly realistically mean? I do get that we could write that statistical statement that I just said about what the parameter estimate quote unquote means, but try explaining that to anyone who isn't a statistician and see how they look at you. Interpretability sucks when we do transformations. It is very, very difficult, especially if we do multiple transformations. Typically for interpretability, what I'll say is if you've done a single transformation, it can make the data or the parameter estimates very tough to interpret. It's tough to interpret single transformations, uh, parameter estimates, excuse me, when your variables have been transformed, even with a single transformation. But with multiple transformations, I tend to think that there is no practical interpretation. That is, there's no way to tease out the meaning of what that possibly means realistically. The one exception to this is if the multiple transformations are guided by theory. That is, if there's a theoretical reason why there should be multiple transformations done on X or Y as we're assessing the relationship with each other. If there's a theoretical underlying cause as to why there should be certain transformations done, that same theoretical underlying cause aids in interpretability because it gives you a mechanism to explain the nature of the relationship after the transformation was done. All right, well, this ends our discussion on remedial measures in simple linear regression. In the next lecture set, we'll be looking at regression in matrix form, and this is what's going to open up the world to dealing with multiple different variables in our regression equation and allow us to jump into multiple regression, which is really opening the Pandora's box of the magic, the beauty, the wonder, the majesty of regression. It really is one of the most powerful statistical techniques we can teach. It's one of my favorite techniques to talk about because it is so broad, so useful, so helpful, so applicable. And actually, through this next lecture set where we talk about the regression in matrix form, it's a bit technical. Bear with me, though, because after we get through that, that's when we just start having fun.